the empirical rule for normal distributions. So if you have a normal curve, and what I think of is if you take all your data, like all the heights of everybody every male in the United States, every female in the United States, whatever you want to do, you collect your data. And if you do this, and it's most of the time it's going to be normally distributed, as long as it's a non-biased survey or non-biased collection of data, and you're going to get a bell curve like this. So if you could imagine that 100% all your data, all your little histograms, are going to fit underneath this curve. So what this follows then is the mean, which is usually written as x bar, is the mean. And then you have the standard deviation, which is lowercase Greek symbol sigma, and that is standard deviation. So standard deviation and mean. And if you remember what standard deviation is, that's the average distance that each number is away from the average. So what they're saying is if you collect all your data, 68% of your data fall within one standard deviation. So if I make a little line here and say there is millions of little dots or bars or however you want to look at it, within one standard deviation, 68% of my data is there. Now within two, so from here, and I could make this so from here to here, so within two standard deviations, I have 95% of my data. And then within three standard deviations, so from here to here, and I'll just do like a little thing out here, that's 99.7% of your data. And they use this to tell, like, if say you have a patient that is experiencing something and you have the data on it, you look and go, oh, that person's sitting way out here, that's extremely rare, that shouldn't be happening. If they're sitting right in here and they're having something happen to them, but it's kind of like what everybody else experiences, then that's not really out of normal. If you have a baby that's a 4-year-old or something that's maybe 5 feet tall, they might be sitting right here. Well, that's extremely rare, so there's something going on. There's something going on that's causing that. Or likewise, if you had a 4-year-old that was a foot tall, there might be something going on, or 2 feet tall, that's causing that. It's extremely rare that they're that short or that tall, and they can do this with height, weight, reactions to medication, all kinds of things you can look at underneath this normal curve. And what I like to do is what I'm going to show you next is I like dividing this thing up. So I have another curve already set up for you, and I'm going to go over here and grab my tool, and I think I have one that'll draw me a straight line. There we go. And I'm going to divide this up. And if you could do this and hang on to it, see, so there's 1, 2. Now looking at this, remember, if this is your mean, so that's going to be your mean in the center, then 50% of your data will be above the mean, and 50% of your data will be below the mean. I know that sometimes can sound a little weird, but they think of it as an infinite amount of data. So let's look at here. Here's our mean. So we're going to call this x bar. I'm going to call this 1 sigma, which means 1 standard deviation above, 2 sigma, because I'm 2 standard deviations above, 3 sigma, which is 3 standard deviations above. Now I'm going to go here and go 1 standard deviation below, so that's a minus 1 sigma. So I'm 1 standard deviation below the mean. Here I'm going to go minus 2 sigma, which will be 2 standard deviations below the mean. Then I'll go over to here and go minus 3 sigma, which is 3 standard deviations below the mean. So now if you remember right, it was 68% of your data was between here and here. So that means this little section right here should be 34%. And you got to always remember that all your data is under here, so that's 100%. So all these numbers when we're done should add to 100%. So then this would also be 34%, because 34 and 34 is 68. Well, if it's 95 from here to here, and you take 95 minus 68, then you will get 27. And then if you divide that number by 2, you're going to get 13.5. So here is 13.5%. And this one here would be 13.5%, because half of that is here. If you added all these up, you should get 95. Now if it's 99.7% of your data is from 3 standard deviations below to 3 standard deviations above, then if you have to take 99.7 minus 95, and you will get 4.7. And if you divide that number by 2, you will get 2.35. So over here, 2.35% of your data. And in here, you'll have 2.35% of your data. Now you still have a little bit of data out here and a little bit of data out here. So to do that, I just do 100% minus the 99.7, and you get 0.3. You divide that by 2, you get 0.15. So over here, you're going to have 0.15%, and in here, you're going to have 0.15%. This is a perfectly symmetric, and it's assumed to be for the empirical rules, and a perfectly symmetric means or distribution. So here's your mean, there's all the things divided up. Now I'm going to show you why I use it this way, why I do this way, what I use it for. So I have a little problem for you. So it says the normal distribution of heights of American women is aged 18 to 24 is approximately normally distributed with a mean of 65.5 inches and a standard deviation of 25 or 2.5 inches, sorry. From the above rule, it follows. So what percentage of women are taller than 65.5? So I look at my data and I'm going to put, well, 65.5 is my mean. So then I'll go here and I'm going to go ahead and just write in 65.5 because that's my mean. So what percentage of these women are taller than 65.5? Is that what it's asking? Are taller? Well, since that's right at the mean and it's right in the middle, and on a perfectly normally distributed, your mean, median, and mode are all right here in the center. So what would it be? 50%. So that answer right here is 50%. Now, standard deviation of 2.5. So let's do the math here. So if this is one standard deviation above, I'm going to add 2.5 to get to that. So I'm going to add that 2.5. And I get, what, 65, 66, 67, 68. So that's where you're, if you had a height of 68 inches, add another 2.5, and what do you get? 70.5, and then you add another 2.5, and you get 73. And if you subtract 2.5, what's that? 63. And then you subtract another 2.5, you get 60.5. And you subtract another 2.5 and you get 58. Now if I did my math correct, there's all your different standard deviations, anything below, anything above, and you put those in. So I always do that when I go through. So now if I look, what percentage of women are between 63 and 70.5? So 63 is right here. And let me grab a different color. I don't know, black. So between 63 and 70.5. Well, that's one below and all the way up to 2 above. So I'm going to go back to this one. One below, right here, So that's 34. And one here is 34. And going all the way to here, 13.5. So there is one below to two above. So I'm going to add that, 5 here, 4, 8, 11, 3, 6, 7, 8. So 81.5%. So 81.5% of women are between 63 and 70.5. What percentage of women are shorter than 60.5? Well, where is 60.5? Right here is 60.5. That's two below. So what percent are shorter? So down here, well, I'll go back here and, oh, here's two below. So I have 2.35 and 0.15 or 15 hundredths. 5 and 5, 0, carry the 1, 3, 4, 5, and 2. So that's 2.5%. So now let's go back. So then that's 2.5 or 2 and 5/10%. So 2.5% of women are shorter than 60.5. So if you picked out 100 randomly picked women, you would get about 2 to 3 of them. You wouldn't get 2.5 of them. You get 2 to 3 of them. And that group of 100 should be about 60.5 or shorter. I hope this helps on understanding how to do the normal distribution and how to do the standard deviations and figure out your percentages.